Welcome back, everyone. I hope you enjoyed lunch. It's been great so far. Let's keep the good energy going here. So now we're going to have 6 talks on a variety of topics, from hardware design to training and new IRs. So our first speaker is Raghu Prabhakar. He's from SambaNova Systems and Stanford. And he's going to be telling us about this spatial programming language and how it applies to accelerators. So Raghu, please.
All right. Hi, everyone. Thanks, Luis, for the introduction. So my name is Raghu, and I'm going to take this opportunity to present Spatial. This is a programming language and a compiler that the team at Stanford has developed. So I'm going to start off by saying that it's a claim with with the obvious disclaimer, saying the future is probably going to be reconfigurable. So this is a slide which is trying to classify the various kinds of architectures that we know that have varying amounts of programmability. So all the way to the left is ASICs, which they're not really programmable because they're built to do one kind of thing. And then as you add more programmability to architectures, there are various flavors like CGRAs and FPGAs sort of lie in the kind of programmable but not really kind of a thing. And then as you go to more flexible alternatives on the right-hand side, you see CPUs and GPUs. But if you look at what most people are doing to get more performance because of various kinds of walls, end of Moore's law, pretty much everything. Anytime you open a computer architecture paper in the abstract, you're going to find these words. People are moving towards more reconfigurable architectures. So Microsoft released a soft architecture which is implemented. It's called Brainwave. It's implemented on Stratix 10 FPGAs. Baidu announced something last year, and CGRAs are making a comeback. So we published a paper last year called Plasticine, and they all boast pretty impressive numbers, either in terms of performance or performance per watt. But the underlying problem with most of these architectures seems to be that they are really hard to program. Some people who know FPGAs a lot, they probably like the pain, I guess. But I'm assuming if you unleash an FPGA onto software developers, it's going to be a fun experience. So the next question is, I guess, if we really want to keep the performance benefits, but also unlock or democratize FPGAs to software developers, the question is, how do we make it more programmable? And I'm going to go out here and say that if you want to make things programmable, we need this golden triangle, which is a combination of the 3 Ps: performance, productivity, and portability. So, and if you take a step back and look at how people program reconfigurable hardware, let's take FPGAs. Let's pick on FPGAs for now. There are really 3 different ways that have been, 3 different classes of efforts. So the first one is, various kinds of hardware description languages. Verilog, VHDL, Chisel, BlueSpec, this thing called MyHDL. There are many various kinds of wrappers in higher level languages for these lower level descriptions. Now they're great for performance. You can implement whatever you want in these languages. They're very flexible. The problem is they aren't that portable. If you move from one vendor to the other, there are a lot of things which you'd have to either rip out, or you'd have to build like shims and invest some effort and manpower into this thing. And they aren't productive either. I mean, if implement a matrix multiply from scratch, it's probably going to take a week or so, something like that, on any FPGA. So over the past decade or so, there's been a lot of progress made in high-level synthesis, which is C to Verilog, where C with some hints to Verilog or RTL. Now these tools are much better in terms of I guess level of abstraction. But performance-wise, for those of you who've used HLS, you know that it's easy to get to like a 50% zone to get something working. But if you really want to get that performance, the last mile, you have to handhold the tool pretty much through the, to an extent where it doesn't look like C anymore with all the pragmas. Portability-wise, well, yes, you're writing C++. So as long as you stay within the single vendor, you don't have to change your program. And productivity is where I think the big win lies. Yes, you express your programs in terms of nested loops. So if you're a software developer, this is like familiar territory for us. But the problem is, if you would like to delve down one level further and implement various kinds of pipelines, this causes problems. So what we really want is we need something like an improved HLS tool where everything is green in this triangle, or as much green as possible. So we need a tool where we can get more performance. And I think this is a sentiment that's come out in other talks in the past as well today, where the tool or the compiler has to be aware of the memory hierarchy of the architecture you're compiling. There's various levels of pipelining in pretty much any application that you can accelerate. So your tool has to be able to exploit that. We don't want a tool that is specific to a particular vendor. We want it to be portable. And finally, we want people to not specify every last level of detail. We want things to be programs to be expressed at a higher level of abstraction, and we want it to be productive. And to drum roll, this is what we started with, and we ended up with a language called Spatial. And the reason it's called Spatial is because it's for spatially reconfigurable architectures, so something like that. So we have constructs to express pretty much everything I talked about. I'll go through an example in the next few slides. There is also APIs which manage CPU to accelerator communication. So most of that is hidden. All the lower level details and the panes are hidden from the user. And our goal is, it allows programmers to focus on, quote unquote, the interesting stuff. If you are building a neural network accelerator, you want to be thinking about how to parallelize, how to structure your loops, not about how to, resolve a hang in a DMA engine. That's not what you want to be spending your time on. This tool and language is open source. It's the website. Please go check it out. Fork it on GitHub. Give it a shot. There are tutorials and some features that you can try out. So I mentioned memory hierarchy earlier, where the compiler has to be aware of memory hierarchy. So Spatial's abstract machine model, or the view of a generic accelerator architecture's memory looks like this. So there are 3 levels in the memory that it understands. There's DDR, or this corresponds to something that's off-chip. And then there is SRAM, that's something that corresponds to on-chip. And then there are local registers. As you can expect, in most architectures, the sizes roughly correspond to this, this flow chart. And the way you would express something like this in a spatial code is you explicitly allocate where your array resides. For example, if you want a DRAM array, you allocate using a line like that. If you want SRAM, there are different variants of SRAM that are natively supported in the language. So if you want a generic scratch pad, you just call it an SRAM. If you want a FIFO, you call it a FIFO. If you want to do line buffers to do things like stencil operations, you instantiate a line buffer. There are many more. It's in the website. You can check it out. And the transfers between various levels in the hierarchy is explicit. So if you want to move something, a block of something from off-chip memory to on-chip memory, it's explicitly captured. And more importantly, the type of memory access pattern is also explicit. So if you're loading a block of a tensor, then that memory transfer is more or less a regular or a well-behaved access pattern. So that's what is referred to as load in the slide. Whereas if you're loading an array of pointers, if you're doing indirect loads, that's called a gather operation. This information can be taken by the compiler's downstream passes to optimize and instantiate the right kind of hardware. And finally, to instantiate local registers, there are these registers and register files and shift registers and so on. To express control flow, we all like loops. So Spatial still has a notion of loops. The only difference is, Spatial takes inspiration from parallel patterns, where a parallel pattern is basically a special kind of a loop where you know certain other kinds of properties on how to parallelize it. For example, here, if you want to do a reduction to do something like a dot product or an A plus B, you instantiate the loop as a reduce, and each loop has an implicit parallelization factor associated with it. So this is an auto-tunable parameter that the compiler implicitly records and then figures out the right value for as you proceed. There are different kinds of controllers. What I mean by that is if you write a loop, the way you would want to run the loop can be different. So you may want to run it as in a streaming fashion, where you want to run the loop iteration the moment data is available, or you might want to run it in some sort of a pipeline fashion or in a sequential fashion. The buffers and loop sizes, etc., they're all explicitly declared. Because if you're instantiating on-chip memory, you have to know the sizes of the memory ahead of time. The third and final thing that I want to highlight here is that if what goes hand in hand with parallelizing a loop on an architecture is also banking the memory such that you should be able to feed the beast. So based on your access pattern and the parallelization of a loop, Spatial automatically figures out how to chunk up the on-chip memories that has been allocated. So I want to give a quick example with sort of a step-by-step anatomy of what a spatial program looks like. So the slides are, it's a very simple example. It's dot product. The reason I picked a simple example is this is the only thing that actually fits in a slide, the picture and text included. So, so to start off with, you're trying to take two vectors, A and B, as denoted by those two boxes there in DRAM, and you want to compute a scalar result, which is called an argout here. Now, argout can be thought of as output arguments from the accelerator. So these are explicitly declared. And then there is the language requires you to declare a scope where everything that will get accelerated on the FPGA or CGRA gets put in. So this way, the work division between host and accelerator is explicit. And then there is the outer loop, which is a reduction, because you're trying to take n number of elements and you want to combine them to one element somehow. So that's what the reduce tries to signify. And then in the inner loop, you declare some local memories. Here, tile A, tile B, and ACC correspond to blocks of the outer loop components that you saw. And then there is the explicit load from vector A to tile A, vector B to tile B. And finally, there's the inner loop, which is also a reduce, where you're computing a partial dot product of tile A and tile B. So the way this code is written is that you bring in blocks of A and B, do the partial dot product, and keep accumulating the results until the final result is ready. So what you see on the left here is actually a fully legal spatial program that compiles. And on the right-hand side is like the data flow graph that it's describing. And the final reduce is, instantiates another adder. So what I've not shown in this picture is that every level of the loop, meaning the reduce, outer reduce, inner reduce, the loads, they're all special kinds of loops, and they all have implicit design space parameters that the compiler captures. For example, what is the size of A? What is the size of B? What is the banking strategy? Do you have to double buffer it or not? Do you have to pipeline the loop? How much do you parallelize the outer loop? How much do you parallelize the inner loop? All of these factors, they are captured implicitly as design space parameters, which is then fed to a design space exploration tool. So that's the language. Now, the compiler begins with that as the input. Now, it's an embedded DSL in Scala, but then this is turned into spatial IR by the compiler, and then there's a slew of analyses that we do. So those are all the analysis passes that happen inside Spatial. Even this is a subset of what actually happens, but I'm not going to go over all of these details. This work has been published in PLDI earlier this year. The paper has most details, but I'd like to highlight a couple of things. The first one is control scheduling. What I mean by this is, in the dot product example, you saw that there's an outer loop and an inner loop, and in any real-world application, like neural networks included, you have a lot of nesting of loops. And it's likely that you can implement each loop level as a pipeline. So in reality, an accelerated application on an FPGA will likely have pipelines at multiple levels of granularity. And the control scheduling takes care of organizing the tokens and data dependencies between these levels. One thing to point out here is we tried using commercial HLS tools to do something like this. HLS tools also can pipeline loops to some level. But if you can create an arbitrary loop nest, it's easy to confuse the tool. It's just the nature of what the tools are built for. And the next thing that I'd like to highlight is the design space exploration that I talked about. Just to recap, this was I've simplified the block diagram of dot product here. What we'd like to explore is design space, which is something like how big should your tile size be? Should you have to double buffer it or not? Do you have to parallelize it? And if you parallelize it, you have to construct a reduction tree of adders and a SIMD multiply unit. And based on how much you parallelize, you have to bank it. And when you bank it, the number of ports you need on FPGA or any resource would change. So all of these things have some associated cost, and the cost is dependent on the architecture. So we manually exploring these things is it's pretty hard. So we have a design space exploration tool. Not going to go through the details here, but there's more details in the paper. But the abridged summary is the approach taken is more or less similar to the online learning method that was described earlier. And the online learning method periodically samples and updates a model internal to the compiler, and it's pretty fast. When we compared this with like vanilla HLS, where we were evaluating things in the critical loop, we got some crazy speed up of like 6500x. It's because the techniques are different. And then the rest is, well, after all the optimizations, we produce Chisel, which is sort of a Scala-based HDL from Berkeley. And we produce whatever is running on the host, the management code, C++ is produced. So we wanted to evaluate this. We support a few variants of Xilinx boards and Altera boards. But for evaluation, we wanted to check how, what is the difference between us and, because we've picked the Amazon F1 instance, what's the difference between us and SDXL, for example? So we hand-optimized SDXL examples, picked something from their open source benchmark suite, and Spatial was handwritten by us. And if we compare the execution times, depending on the application, the speedups can vary, but most of these speedups are due to the fact that Spatial was able to tune the sizes of the memories and all that better than SDXL, and for most of these applications which have higher speedups like GDA and Smith-Waterman, they are implemented as nested pipelines in SDXL, which doesn't take advantage of coarse-grained pipelining. But the rest of them, for example, Query 6 is a memory-bound application, so it's both Spatial and SDXL do an equally good job at utilizing DRAM memory bandwidth. So we also wanted to measure productivity. For lack of a better measure, we measured it using lines of code. If you think it's a questionable measure, we can talk offline. I may agree with you, but unfortunately, we don't really know of any other better way of measuring it. But on an average, if you compare an SDXL program and a Spatial program, I promise we didn't add like random comments or lines just to inflate this number. We're about like 42% better. And portability-wise, we took the same Spatial program and optimized it for two different Xilinx variants. One of them is the Zinc 706, which is a smaller FPGA, and then the Amazon instance. So without changing anything, just by recompiling the same Spatial source code, we were able to get some amount of speed up just by moving to an FPGA, because we were able to meet a better timing on the F1, and it has a higher memory bandwidth. Now, when we tune it, this is where you see the real speed up, right? Just by tuning, there was an additional amount of speed up as shown in the red here. So the total speed up is, if you multiply the two, the green bar shows speed up between the smaller FPGA and the larger FPGA. And this is not just unique to different FPGAs. We also took the same source code for different applications and compiled it to the CGRA that we have built in-house called Plasticine. And you can see that you can auto-tune the same applications to maximize the resources on Plasticine. It's unfortunately hard to do an apples-to-apples comparison with different kinds of CGRAs because most of them are academic prototypes. But what we can say here is we are maximizing the resource that makes sense for that application. Finally, I wanted to touch upon some ongoing work now. So given that this is the infrastructure that currently exists, and it's open source and it's being used in Stanford for different classes, we wanted to marry the benefits of Halide to Spatial in order to produce hardware. I'm going to skip what is Halide. I think most of us know what it is. The question is, why do we need Halide, and why does this connection, what does it buy us? Well, one, given that TVM is mostly using Halide's concepts of algorithms and schedules, and they operate at different levels of abstraction. It seems like Halide and Spatial have good separation of concerns. Halide can do loop-level transformations, tiling, design space exploration at that level, and Spatial can do the lower-level target-specific loop design space exploration. There's some interplay between this. We still have to figure out whether, how exactly it's going to work, but it's an open, ongoing research project. And both of them have loop-based IR, so it kind of looks like that. So just as an example, the goal is to take Halide program as shown in the left here, which is mostly, it's trying to do a stencil operation, and produce Spatial like it looks on the right-hand side. So if you'd like to talk about this, more details about this, please come talk to me offline. But that's all I have. I'll be happy to take questions. Thank you.
All right, everyone, it's time for one question while we do context switch. Any questions for Raghu? Yeah, Kiran.
Hi, thank you, Raghu, for the nice presentation. I have one question on the plasticity.
Yeah.
So when you compared that speed up for the plasticity, did you have a prototype of plasticity in ASIC, or how did you get that benchmark?
So we have plasticine implemented in RTL. So it was through VCS simulation.
Okay, got it.
So it's DRAM was modeled using DRAM sim.
Okay.
So DRAM bandwidth is as accurate as the simulator.
Got it. Thank you again.
Great, thank you. Maybe later. All right, okay. The next speaker is Justin Gottschlich from Intel, who's going to be telling us about machine programming. Justin, thanks again for coming. All right, so this works.
Okay, perfect. I think maybe I'll use this so I can walk around a little bit. Let's see. Perfect. So I'm Justin Gottschlich. I'm from Intel Labs, and I'll be talking to you about this problem. Essentially, we have a software programming resource problem. And to put this into context, there was this article at Bloomberg earlier this year talking about how we're at this really big economic boon for technology, yet we just don't have enough programmers. And if we start to look at some of the estimates that we have with our global population for 2019 versus the number of programmers, we can see that we're a very small fraction of programmers here, which is rather unfortunate. To put this into context, if we look at something that's maybe a little bit easier than programming, driving, we can see that worldwide we have about almost 16% drivers. And if you were to see this visually, what this looks like is this. That's a pretty stark contrast. And so primarily that's what I'm going to talk about today. Hopefully you can see that there's this big divide that we need to bring up. And I think that's pretty much all I'll do to hopefully motivate the importance of this problem. So the question is, can we make programming as simple as driving? And what do we need to do? And some of you may be saying, well, you know, programming is much harder than driving, right? Okay, yeah, I get that. So let's just do a quick survey, right, to make this a little interactive. How many of you drive automatic vehicles? Cars that you put into a specific gear? Great. Okay, how many of you can drive a manual car? Okay, great. So I would sort of liken that to many of us can probably program in these higher level programming languages like Python. Many of us can probably program in assembly. Doesn't necessarily mean it's a good idea. Okay, so we can look at driving a car as being a very hard thing if we think about manual, but if we raise the level of abstraction, it becomes much simpler. And can we do some similar things with programming? And so we'll focus on these two areas, reducing the intention challenge and then trying to delegate most of the work to machines. So let's do a quick analysis of what this looks like. So we're going to pit a human against the machine. What we do today mostly is human programming. Not entirely, but mostly. And this is essentially pick your favorite programming language. This is how we describe our intention. And then there's lots of pros. We have complete control, generally. You know, there's stuff happening at the compiler level that may be out of our control, stuff that maybe we like or dislike. But overall, we have a lot of control. The downside, though, is it can be very expensive. Expensive in terms of time, expensive in terms of correctness. It can be slow, error-prone. The biggest problem is that it's constrained by the number of humans that can write code. this is a problem. Whereas if we look at machine programming, and what I mean by machine programming is here, is that the software is being developed at least somewhat, potentially fully, by some autonomous system, probably using some form of machine learning. And classical compiler transformations, IR transformations, are generally fall into this category, but we have an emerging area as well. You can think about verified lifting that Alvin Chung is doing, the auto TVM stuff that we've heard quite a bit about today, which I'm a big fan of, and so on and so forth. So there are emerging things happening both in academia and in industry. There's some major pros to this approach of machine programming. The biggest, in my mind, is that we're no longer constrained by humans, we're constrained just by compute. With that said, there are disadvantages, right? There's no such thing as a silver bullet. And so right now this field is fairly immature. If we do it mostly through machine learning, it may be stochastic, at least partially in nature, which is going to give up some of our control. But so now let's dig a little bit deeper into this machine programming. So my colleagues and I, Intel and MIT, earlier this year we published this paper called The 3 Pillars of Machine Programming. And that essentially is what we show in this diagram here. The 3 pillars fall into these 3 categories: intention, invention, and adaptation. And I'm going to talk a lot more about these details and give concrete examples throughout this talk. But very, very briefly, sort of superficially, intention is what we do right now when we write code. It's the idea that we have some idea in our head that we're trying to convey to the machine, and we want it to be able to do this thing. This is essentially our programming languages. But I think we can do a lot better. The next is invention. Invention principally has been done by human beings. I would argue, with the advances we're making in machine learning, this will change significantly. And hopefully I can motivate you with a really interesting example. We're just on the tip of the iceberg with intention. There's a lot more that we can do. And lastly, there's adaptation. Adaptation is the notion that once we have the software, and it's working sort of the way that we want it to, we deploy it. And to all of us that are actual software engineers that have done engineering work, we know that once you deploy the software, you're not done with it. You're just getting started, right? You're going to have to maintain it. It's going to have correctness bugs, performance bugs, security issues. And that's where adaptation falls into. And then as you can see, all around these things, aside from these specific examples, is data. Data is essentially the key driver for all 3 of these pillars. Without the data boom that we're living in today, really none of this would be possible. Okay, so let's look at a couple examples. So I have a few of my favorite works here. Let's just start walking through some of them. So in the intention space, again, this is where the programmer is trying to specify what he or she is trying to do. We have this famous work by Sumit Gulwani, Flashfill. If any of you have used Excel, you may be already using this. And what it does is basic pattern recognition. You provided a whole bunch of examples on what it is that how you're going to store your data, and then you specify the beginning of some transform. And very quickly, Flashfill can deduce what it is you're trying to do and give you suggestions. So this is one example of sort of raising the bar. This is machine programming, right? These are baby steps, but it's happening. The next example that I'm really fond of is sketching by Armando Solar-Lozama, and I mentioned his advisor, Roz Bodek, because Roz is a professor here. What Sketch does is very similar to Flashfill in the sense that you have some body of code, but it's not complete. And it can intuit exactly what it is that you're trying to do. Now again, it can't do it for large programs. There's only pieces that it's trying to fill in, but it's again the beginning steps of trying to capture this intention. What I really think that we need to do, where I really think we're going, is we need to broaden the space to where everyone can be a programmer. That literally we do what my colleague Tim Matson calls is Star Trek programming, where I start talking to the computer and saying, computer, I would like you to do this. And then what happens is the computer realizes we've given it a partial specification. And then it comes back to us and says, well, you've only specified this, what do you want us to do here? And so we have this dialogue, conversational programming. We raise the level of abstraction. So the next area of work is invention. This is actually my favorite pillar. In my mind, this is the hardest pillar to make advances in, and most of us really aren't doing much work in this space yet. But there's a really important paper that just came out recently by Tim Kraska and Jeff Dean and a bunch of people from MIT and Google. It's this case for learned index structures. If you haven't read this paper, I highly encourage you to check it out. The high-level notion is just take these existing data structures and then find some place where we can make advances. If we just look at this hash map, it's very trivial for us to look at this and say, this hash function is basically just a heuristic. It's a heuristic that a human built based on some idea that he or she had on something that might work. But if we replace this with a model and we vet it with some data, a priori, that's going to be similar to the data that's going to see, we can get significant efficiency improvements on this existing data structure. Now, what I envision with invention is going much further than this. It won't just be a piece of the data structure. It will be the entire data structure. There will be new containers. There will be new search algorithms. All of these things invented by machines. Right? And one of the beauties of machine learning that machines have over us is a lot of times as humans, we're constrained in the way that we search through problems based on what we think is logical. This is a good thing and it's a bad thing. Machines don't have this bias. So they are willing to explore spaces that sometimes can lead to really valuable information that as a human we would completely ignore. And then last we have adaptation. So adaptation is probably the easiest to make advances in. Auto TVM is an example of adaptation. I'm going to talk a little bit about the work that my team at Intel Labs and collaborative work with MIT is doing on the adaptation pillar. So let's go ahead and dive into those examples now. So the rest of this talk really will be focusing on adaptation so you can see a little bit more what's going on at Intel Labs and some of our collaborations. So remember, adaptation is this notion that we're going to evolve the software, specifically in these spaces. It's going to repair, optimize, or secure the system, and it's going to do it in an autonomous fashion. Well, one of the first things we realized when we looked at the adaptation pillar is that most of the problems you find in adaptation are anomalies. And it turns out that the traditional ways that we evaluate anomalies using classical metrics like precision and recall don't work for the anomalies that we find in machine programming. For example, bugs occur over a period of time. It's not a single instruction. It's usually many instructions. Security exploits are the same way. Performance degradations are the same way. So what you need to do first is look at the metrics that we use to evaluate our anomaly detectors and rewrite those rules. So for example, if we look at time series anomalies, we can see that we have partial overlaps of real anomalies and the predicted anomalies. So what does it mean to have a true positive and a true negative? And you look in the space of point-based anomalies, it's very simple. It either falls in this space or this other space, but you can have partial overlaps in the time series space. This is a problem, because if we can't properly evaluate our anomaly detection systems, we can't possibly build anomaly detection systems that are going to be accurate. So what my team and I did is we basically looked at the state of the art. We realized that it just doesn't solve this problem. This is not necessarily a flaw of the prior work. The prior work just wasn't aimed at solving this problem. So we realized that we needed a new accuracy model. So we built one. This was featured last week. I was hanging out with Luis and several others in the room, Montreal, and we presented this work where we've redefined the core evaluation metrics for anomaly detection. You see this little BMW thing here. This is to demonstrate this isn't purely just academic work for the interest of publishing papers. We actually are delivering and have delivered this research to BMW, and they're going to use it for their time series anomalies for autonomous vehicles. What's interesting, though, is when we first presented this to BMW, they said, hey, these equations, these are great. We're not mathematicians, though, so build a software that'll actually do this so we can just use the software. So we did that. We built the software. And the software now is not only available to them, as of last week, it's publicly available to everyone. So this is open source. I'll publish these slides on my website, but if you go to this GitHub link, you'll get access to the source and you can start using this today. There's several examples. So delivered to BMW. So that's the first piece in the anomaly detection space for the adaptation pillar that we start to investigate. And not only is this beneficial to the space of machine programming and to autonomous vehicles, it's really helpful for Intel. You may have heard of these two things, you may not have heard of these two things, Spectre and Meltdown. It's a little embarrassing, hey, it happens. So we're working on solving these things. One of the ways is having really good anomaly detection systems so we can detect when these types of attacks are happening. So Intel is using this not only with our business partners, but internally. So I'm working very closely with the cybersecurity team, building state-of-the-art models using these type of evaluation systems. So one of the other key areas that we have that's very interesting for both anomaly detection and neural networks is this notion of interpretability. So in many cases, you can have anomaly detectors that say, hey, there's an anomaly. Or you can have a neural network that says, hey, something happened. But then if you try to understand why that thing happened, you won't know. So what we did is we teamed up with MIT, and we took our autoperf system, which is a zero-positive learning autoencoder. Zero-positive learning is a subset of one-class classifiers, if you're familiar with that stuff in machine learning. And essentially what autoperf does is allows us to identify these concurrent parallel software anomalies, performance bugs. The problem, though, is it can't tell you where the root cause is. But if you look at the Polaris system that MIT has built, that's specifically what it does, is it's focused on interpretability. And this was presented at NIPS last week, so not to appear, but has appeared. So we thought, what happens if you combine these two things together? If you use the autoperf system to tell us where the anomalies are, you use the Polaris system to tell us where the root cause is, will this work? So we put the system together, and it turns out early results, right? I'm not going to generalize this, this works for everything, is we can take a parallel software bug for performance. We can identify this anomaly over here, that's what that point is. Autoperf system detects it. We then use Polaris to identify what the non-anomalous space is, and then Polaris essentially says this is where you need to go, and now we can move that anomaly into that space. So we nearly have round-trip, fully automated adaptation working. We don't have the final piece, which does the automatic integration of the fix, but we do have root cause analysis now, which is really important not only for anomaly detection, but for neural network interpretability. Because this is a TVM conference, I felt it important to also draw attention to the excellent work that UW and several other people are doing in TVM, specifically auto TVM. I would also consider this adaptation because we're using this machine learning system to find these optimizations. And as Eddie and Tanchi and several others have already referenced, this does very well, right? Lower is better in this case, and you can see across the board, auto TVM is performing fairly well. However, that doesn't necessarily mean that auto TVM is going to be the best thing. If you look at some of the work that my lab is doing at Intel, our PCL, Anand is one of the people that's driving this. If you want to have more insight into it, please talk to him. Anand, do you want to just wave your hand? Perfect. So that's Anand, and we've shown that we can actually improve the performance of TVM quite a bit ourselves. So what would be really interesting for the next work of auto TVM is to compare it against these highly optimized schedules and see how we can, what the performance looks like. So in conclusion, we're arguing that machine programming is coming. There's a lot of you that I'm collaborating with at UW. I work really closely with Stanford and MIT as well. In addition to numerous people at Intel, we're really behind this. We think that this is going to be the new shift in writing software. If you're interested in this, please let me know. In fact, I've been asked to teach a new class on machine programming at Penn that we'll start recording soon. If you have ideas on how we should introduce this topic, please let me know. I'm already working with Alex Ratner and a couple other people from the Stanford Software 2.0 group that are helping me construct what this syllabus looks like. And then last but not least, we have a machine learning and programming languages workshop that we created back in 2016. It's in its third incarnation this year. It'll be a workshop at PLDI, but we are planning on breaking it out into its own conference, much like SysML has done this year, or last year, but officially this year with full papers. I've been on the steering committee and program chair, general chair for MAPL since its inception, and I know that Jared, are you in the room? Okay, Jared had a paper this last year, but I would love to see a TVM paper more than just, what's Jared's systems again? Relay, just Relay. So our papers are going to be due at the end of January, February, so you guys have lots of time. So if you're interested, please feel free to submit. And just a heads up to the general chair and the program chair, Tim Mattson from Intel Labs, and our program chair is my good friend Armando Solar-Lozama. And I believe that's it. Thank you.
Any questions for Justin? Yeah, absolutely. All right. Just keep the mic.
Yes. So, so on the third slide, right, you mentioned like we have 18% drivers and 0.3% programmers. Let's say if you look in terms of the future, let's say 2050, you probably would have a close to 1% driver because of the self-driving.
Yeah.
So, and also when you're saying that you're doing a machine programming, so you want to reduce the programmers, what is your take?
So, yeah, so that's an excellent question. So to repeat his question real quickly, he's basically saying that with autonomous vehicles, we're getting to the point to where we would have no drivers. It would just all be done autonomously. And so is the point to bring down all the programmers to zero? Well, I don't think so. In fact, I think that the key thing is we want to make everyone a programmer. We're going to automate a significant amount of the space, but the intentionality of the software that we're building, that's going to be human driven. And so what I really want to see is that we broaden the funnel of that space, bring that up to 100%, but hand off most of the work to programming to the machines. Yeah. Okay, thanks.
All right, thank you, Justin. All right, so and continuing the blue theme of the slides and Intel, now I have a talk from Brian Retford from Intel. He's going to be talking about PlaidML. Thank you, Brian.
Yeah, thank you. Thanks for having me out to talk about PlaidML, which is the other tensor compiler, which happens to also be based out in Seattle. So I'm the former CTO of Vertex.ai, which Intel bought recently, and we were working with the Movidius and Nirvana teams to further hardware and software co-design. So I want to briefly talk about PlaidML's domain-specific language because it has one characteristic that I think is interesting. In general, you look at sort of all tensor compilers, they have some kind of MapReduce or tensor algebra language. PlaidML's looks goofier than other people's, but it does have this useful property that the tensor language itself is differentiable. So you can actually, if you want the, there's a dilated striated convolution up there. If you want the derivative of the first input with respect to the output, you just sort of swap the two expressions, and you magically get the derivative. So I'm going to talk a little bit about PlaidML v0, which is the one that you can download and use today. Oh, there's a lot of text up there. So we just released it, relicensed it under the Apache 2. It was AGPL'd when we were a startup. I don't know if that was a good idea. We have a reasonable community. It's nothing like the amazing TVM community here. And we support pretty much every framework as soon as our upcoming ngraph backend is released. So you can train or do inference via pretty much everything. You can't train via PyTorch yet. It's performance portable for major GPU architectures, which is to say that we have a bunch of configurations that describe sort of different GPU architectures, and then we automatically generate kernels based off that. And in practice, we see results that are somewhere between like half as fast and occasionally sometimes faster than AutoTVM. The current version of Plaid is not particularly well suited for accelerators or other architectures like that because the sort of hardware model that's hard-coded in it is targeted towards GPUs. The one thing that we definitely have going for us, I would say, is a cuter logo. Okay, so it's so cute, it doesn't want to advance to the next slide. Okay, so PlaidML, the current version of PlaidML has this sort of really just spaghetti code together that represents these sort of 5 passes that are all driven from, well, the tile DSL and some settings that describe the accelerator that you want to run it on. And you can see the very well-named and informative settings up on the right. So, so basically, these settings combined with a programmatic model of the GPU architecture lets us estimate how much how much a particular layout of a program will cost very quickly. how long it will take to actually execute one of these things. So in PlaidML v0, first we vectorize things. If we can, we find the best way to, like the best dimension to vectorize things on. And then we do an auto tiling pass where we basically consider all the possible tilings of a given contraction, and we hill climb up and look at the cost. Using this cost model, we evaluate how much a given tiling will cost in terms of runtime and memory transfers, and then we sort of pick the top one. And usually, the top one, the best kernel, if we scan through all the ones that we generate, we usually, the best one's usually somewhere inside the first 10. Sometimes you have to go all the way out to like 50. So the model's not perfect. Yeah. So moving forward to the next version of PlaidML, and sort of its underlying abstraction, we wanted to extend PlaidML such that it could actually encompass and represent a broader range of hardware. So Stripe is the name of Polyhedral IR that PlaidML uses in this next version to actually do its optimization passes, which are now sort of abstracted out and configurable. So with Stripe, we can support arbitrary tensorization. We can do complex vertical fusion, so we can fuse multiple convolutions together. And we can support complex memory hierarchies, as well as, excuse me, heterogeneous compute topologies. And then, because we sort of couple these hardware designs with cost models, we're able to estimate and produce performance metrics for pretty much any design of hardware. And that allows us to rapidly do hardware and software co-design. So the Stripe IR is it's fundamentally polyhedral, and the architecture of PlaidML basically now works, and you emit Stripe from your tile DSL, and then it goes through a bunch of passes that emit more and more Stripe that you then eventually lower to any particular hardware target that you're interested in. So conceptually, Stripe basically represents computational blocks that span different ranges of indices. So you can see here on the right sort of a representation of an 8 by 8 by 12 tensor with sort of two block structures. So the outer block, you go over like indices j, i, and k from 2, 2, and 3, and then the inner blocks are all 4 by 4 blocks. So you can see that overall, if you traverse all of these indices in a nested way, you eventually traverse the entire tensor. So these blocks, they have indexes that define the ranges of the computations that will be performed in these blocks. They have constraints that further limit the bounds of the computation. And then they also sort of reference tensors. We call them refinements. It's basically, if you can think of these inner blocks as having, basically representing a view of the outer tensor. And this particular structure lets us do a lot of optimizations, and we'll sort of detail what some of those look like in a second. So this slide has a bug in it, but I can debug programs, but not slide decks, apparently. So yeah, tile code is very important. It's just going to stay up there the whole time. So Stripe operates off of these tags. The screen's very small. The tags basically inform the optimization passes as to what's going on. So they provide semantic context for a given block that is then used to determine, that other passes can use to determine whether they should be mutating this pass or not, or mutating that block. It contains allocations. So these are basically the tensor inputs and outputs, and their sizes and strides. These ones are all allocated at address 0 because they haven't been located to a particular memory element yet. So these are refinements, which I was mentioning earlier, are sort of views of tensors that are implicitly like bumped through the tensor space as the outer indices proceed. These are the indexes. So you can see this is a 3 by 3 channelized convolution over a 1024 by 1024 image with 32 input channels and 64 output channels. And so these are the constraints also. So basically you can set any set of polynomial constraints, and that specifies that the computation that's contained inside this block should only be executed if these constraints are true. There's the tile code again. So we, in order to keep the IR single static assignment that you see below, we, and to simplify that situation, we specify on the output tensors basically an aggregation operation. And then we have this single static assignment intermediate language down here. All right, so I'm going slower than I meant to. OK, so Stripe works off of effectively models of hardware. So you can see, as compared to the PlaidML v0 model, here we actually enumerate various memory units, execution units, and transaction units. And so this is sort of a model of a hypothetical accelerator with DRAM, SRAM, and like 2 different computational units glued to those. In addition to that configuration, we basically have a set of passes that describe the various optimizations that make sense for this particular hardware target. So the key takeaway from this design is that if you're actually trying to build hardware, it helps if you can iterate through the hardware design space and explore as much of it as possible. So Stripe greatly simplifies that by allowing you to specify the hardware in this very, very high-level language. And then combined with the sort of optimization passes, it creates effectively a compiler that does automatic scheduling and automatic kernel generation for your hypothetical hardware architecture. And then you can easily measure how long, how well different workloads would perform without the need to actually instantiate the hardware. So we're going to look at like tensorization. So in this example, we have a configuration of a machine that supports 2 different kinds of stencils, like a 32x1 stencil and a 4x4 stencil. So given this information, Stripe will, or PlaidML optimizer for Stripe will figure out the best way to, like the best stencil, given the set of stencils that it has, it will pick the best tensorization that makes the most sense in terms of overall cost. So this is just a quick example of, this screen is really hard to read, what the Stripe looks like before you tensorize it and after. And you can see that effectively it's added an interior block that has tiled over x and y in chunks of 4. So PlaidML, as I mentioned, has this sort of hill climbing algorithm for determining tiles. So in Stripe, you can arbitrarily add auto-tiling steps, and you can effectively tell which memory bank you want it to tile things over, so it can figure out like how big that memory bank is. So it will figure out, basically, again, comes up with a table of tile costs, picks the best one, and then tiles your computation over that. And I'm going to skip that for now. So as far as fusing contractions go, say you have 2 convolutions, a 3x3 followed by a 1x1. It turns out that it's frequently useful to actually, rather than doing one convolution and then doing the next one, if you chunk the entire thing up and just do one chunk all the way through to the end, you can actually get increased performance. So Stripe lets us do these kinds of analysis, and we can actually break up. So you have like 2 convolutions there. You can actually effectively squeeze them together into one convolution over a broader range of indexes. So, so this code is all pretty new. A bunch of it is upstreamed. There's nothing that actually runs it available yet. All that's coming. We'll be porting sort of the old Stripe models into the new one soon. And we'll have a paper coming out next year. And if you want any more information, you can email Tim, because I'm going to Tanzania tomorrow.
Any questions for Brian? Well, we want to see Jared. Where are you? Questions for Brian? Yeah, right there.
So for the last part, like you just say about breaking the convolution into small pieces, and then you can go like vertically. So for that part of code, is it available online in your repo yet or not?
Sorry, say that again. I couldn't understand you.
The breaking up the convolution into small pieces and then do the fusion vertically. Like the thing you showed in the last slide. So is that part of code available online now or not?
Yeah, the fusion passes are there, and there's a test actually.
It's in your GitHub. Is that correct?
Sorry?
Is that in your GitHub
yeah, it
repo?
is. It is in GitHub. I can, if you talk to me later, I'll show you where the code is. Yeah.
Nice, thanks.
Yeah.
Okay. And now I know you've heard about Relay quite a bit. You've heard the term. Now you're going to hear a lot more detail about it, right? You sent me a second one, yeah. The cloud is magic. Things appear here in my laptop. Great. All right, Jared, here you go.
All right, awesome. Thank you.
Hey everyone, I'm Jared, and I'm back again to talk about Relay. So Relay is a high-level differentiable IR, and we're going to spend the rest of the talk unpacking that. So first to start off, even though I'm giving this talk alone, this is not work that I've done alone. This represents lots of months with lots of people. There are also a bunch of community members and a few others who have contributed in small and big ways who are not on this slide, but thanks to all the other people who have helped contribute. So the first thing I want to do is kind of unpack the stack diagram that we've had up here this entire time. So we've been looking at this, we have this new bullet point on the stack diagram about having a high-level differentiable IR, and that's what this talk's going to be focused on. So really the question that we are interested in here is how do we represent deep learning computations? So, as you all know, we use deep learning to build these parametric functions, which are hard or impossible to program. And in order to represent these, we need a representation for the computation, we need a way to differentiate them, and we want a way to optimize them in the mathematical sense. So what we're really going to focus on today in the course of this talk is the first bullet point of how do we represent computation. So the existing approach that everyone here is very familiar with is the approach taken by NNVM, TensorFlow, and many other frameworks, where they have this sort of computation graph IR that's at the very highest level. One of the problems with these computation graph IRs is that representing certain things is challenging often. So for example, if we want to represent a training loop in these computation graphs, it's very tricky to express or impossible to express some of these programs. So what we're really going to look at today is how do we go from the existing approach, oh, there's a typo here, existing approach to the goal of having a high-level differentiable IR. So you can see we went from dotted arrows, sometimes it works, sometimes it doesn't, to we want solid arrows where these programs can always be ingested into the IR. So roughly, we can look at a lot of the previous approaches as having this sort of split model of computation. So here, the darker color is Python code, and the inner color is Relay code. So in the world that we would want, that the frameworks currently inhabit is this left-hand picture, where the outer loop, when you use for training or used for generation, when you're using a generative RNN or control flow, or even in PyTorch, exists in the Python interpreter. So if we want to execute a fragment of code in the IR or in the frameworks such as in PyTorch or TensorFlow, we write a loop outside which calls into this inner blob of code in the lighter shade of purple. And what we want to do is go to the right-hand side picture where we have a representation of the entire thing, including the loops. And so this is a traditional idea in programming languages where we want to capture your entire program so we can optimize the whole thing and not just a fragment of it. So the challenge is to do this is, you might ask, like, why have people not done this before, is that computation graph IRs have a lot of nice properties. For example, they're pure. Often, there are very few side effects, and if there are, they're well understood and dealt with in the language. They often lack control flow, and the ones that have added control flow, like TensorFlow, do it in this sort of data flow style, which makes it easy to apply certain kinds of reasoning. They lack abstraction, so adding functions in this graph model is kind of weird. You need to add a scoping, so people have built these notions of subgraphs or labeled scopes. But this is sort of ignoring a huge body of work that we know how to do on building functions, reasoning about functions, transforming functions, optimizing functions. And oftentimes they're not recursive. So if I wanted to directly represent some recursive or iterative thing like a loop, I need to either do what TensorFlow does where I elaborate the loop into a data flow graph. But one problem here is that for people writing optimizations and reasoning about the program is the final program no longer has a trace of the loop. So instead I see a elaborated away version of the loop, but I often want to reason about the high level program that I actually inputted as a user. Another challenge here is that most of these frameworks in their IR only deal with the execution of the computation graph itself, and oftentimes many of the details related to training and differentiation sit outside or next to the program representation. So what we would like to do is make this accessible to the user as well. And finally, what we're really interested in doing is end-to-end optimization. So if I can represent the whole thing, what I'd like to do is optimize it in one chunk instead of having to, say, like in the PyTorch example, optimize a portion of the computation graphs that I've extracted from the program. And you might ask if this is a challenge, but for a long time, and this might have been rectified in the recent PyTorch 1.0 release a little bit, but if you use any dynamic features in PyTorch, they would tell you that the exporter, the ONNX exporter will be invalid because they can't actually represent the dynamic behavior of the network in the exporter that they have. So with these challenges in mind, we set out to design Relay to address these challenges. So Relay's goal is to be this high-level IR that sits at the top of the TVM stack. So the goal is that frameworks will export directly to Relay. We already have some initial support for MXNet. We can export NN and VM models, and we can also, there's a prototype TensorFlow front end as well. The goal is once we have that IR is that we want to be able to do automatic differentiation directly on this intermediate representation. So I don't spend a lot of time on it in this talk, but we have a new procedure for doing what we refer to as higher order automatic differentiation. So to unpack that for a second, we can differentiate the full Relay language, and we can do it for nth gradients. So we solve a lot of the problems about computing second order gradients, which are often useful in optimization. The other thing is because we have the whole program representation, including loops, it's possible for us to do whole program optimization. And Relay is a big system composed of an intermediate representation, autodiff, an optimizer, and many backends. Relay that I'm going to talk about today in its current form is open source as part of the DMLC/TVM repo. So go and feel free to check it out. Already some people in the audience are contributors. So our initial results on Relay, and this is from a recent submission we have, are pretty good. We were able to take a whole generative RNN, for example, and take the equivalent program in PyTorch and compile the entire program. We were able to show 3 times performance for average inference time. Then we were able to show that on models that NVM supports well today, like ResNet, we're able to achieve a comparable performance to NVM and better performance in TensorFlow and TensorFlow Lite. And then finally, we're able to integrate with the Vita work done by Thierry and my other collaborators here at UW in order to get Relay onto FPGAs, and we can show an 11 times performance improvement over the baseline. So here's a high-level system diagram of Relay, and I'm not going to go too in-depth on it, but we can briefly look at it. So there's multiple front ends, like I said. There's a way to directly construct it in DSL as you're used to today. There is the model importers that I've discussed, which bring you from other frameworks. There is a textual format, so this allows you to actually write Relay programs like you would program in a normal programming language. And then there's an on-disk representation similar to NVM and LLVM. The main important pieces are the compiler, which we're going to focus on mostly today, and the execution engines, and the rest of the talk will be dedicated to going over these. So the intermediate representation looks a little bit different than what you might be used to. Relay is designed to be a high-level functional language to preserve some of the benefits that we observed in computation graphs. So it's very much similar to the ML family of languages, which the irony may not be lost on you. But its goal is to be tailored to machine learning. So we have features like closures, mutable references, so you can have mutable variables and update state. We have the ability to support data types. We have primitive operators like the ones you know and love, convolution, matrix multiplication, et cetera. And our primary value type is tensors. And I will talk a little bit more about those in a few slides. We can use this to represent the full model. So in the example that we will show in the evaluation, we're able to take in a generative RNN, including the generation loop, and optimize the entire program as one. And finally, we believe the functional style is important because it makes it easy for machine learning developers to write optimizations without having to reason about complex program semantics. And we see some informal evidence of people who've already come out of the community and started writing optimization passes directly for their networks with no prior Relay experience. So one example that I'm going to focus on really quick is an RNN. I assume many people are familiar with this. We can look at an RNN enrolled in time like this. And what we'd like to do is capture this entire thing as a Relay program. And so what we're going to do is we can actually just do this in a functional style. So this program here is a sort of functional loop, which is going to run the RNN to some depth. In the base case, I'm going to return an empty list. So this is an empty list here. In the recursive case, I'm going to run the RNN cell for one step. I'm going to add the output onto the rest of the list, and I'm going to recursively generate a list. And you can see I've omitted the parameters for brevity's sake, but this just encodes a functional style loop, and it's a very simple Relay program. Okay, so one of the other important distinctions that we've made in Relay is that we've designed the IR to be typed. So one thing that previous computation graphs have all focused on is doing shape and data type inference, because this is very necessary to do things like generate efficient code, to run analysis passes to do tensorization and other kinds of optimization tasks later on in the compilation pipeline. And so what we've done is we've tried to make, as we've generalized Relay to a full language, tried to preserve typing for the entire language. The big challenges with doing this, though, is that we want static tensor information. So we want to be able to know, for example, the dimensions of every tensor, but we want to be able to do this in the presence of recursion, in the presence of functions, and we want this information really to be able to do things like match accelerated primitives, sort of the things that Tianqi and Thierry were talking about earlier. The other challenge is that machine learning engineers often expect very flexible semantics from their operators. So example of this is like broadcast or flatten. So these are actually complex functions over the input dimensions, and it's often hard for traditional type systems to capture properties like this. So in order to do this, we designed a type system so we can essentially view tensor type as a function itself, which takes a base type and a shape and is a type. And we can view, like, for example, floating points as things that are parameterized by width and lanes and produces a base type. One important restriction to note here is that we've set up the type system such that tensors can only store things that are of base type, and this ensures that we can always generate efficient code. So you can't do things like create a tensor of closures. So if trying to put a tensor of functions on the GPU or an accelerator is nonsensical, and so we've forbidden that by construction in the language. You can see then when we write a tensor type, it takes a base type here, and it takes a shape. So here, this is an example of a 4D tensor like you might use in image processing, and we capture the dimension statically in the type system. One sort of interesting, unique feature is we've tried to generalize the ability for you to register custom shape inference functions in previous frameworks. We've done this via this idea of a type relation. So really at a high level, what our goal here is that there's some relationship between all the input tensors and the output tensors, and we've been able to capture this property in the type system. So the idea here is that this allows us to solve the problem of having flexible operators. So I'm going to show you two examples right here. One that requires variable arguments, and also the output type is a function of all the input shapes, and broadcasting, which has often been very hard to type in other intermediate representations. So for example, here at the top, we can see addition. So this is broadcasting addition. The idea is that you can give us any type for the left-hand side of addition, any type for the right-hand side, and you can pick any output type, but then we need to assert that this broadcasting relationship holds between the input and the output. So for example, if left-hand side and right-hand side are non-broadcastable, this will not type check. And broadcasting is tricky for those of who are not, maybe not from the machine learning community and not aware of this, because what people want to do is essentially grow the output tensor on dimensions that mismatch. So for example, if I have 345 and n345, the output will be n345. And if I have, for example, a one dimension and another dimension here, I will grow it to match this dimension. And so this is a shape relationship that's actually very tricky to capture in most existing type systems. Another example is concat. So concat actually needs to take some arbitrary number of inputs, but we also want the output to be equivalent to summing the shapes of the inputs. So you're able to capture the same property using the relation system. Relay also ships with quite a number of optimizations. So we spent the last couple months trying to match NNVM performance. So we have reached feature parity with NNVM in just the last week. So we have all the standard optimizations that you are aware of, things like fusion and constant propagation, and these are just a couple examples. And then we also have accelerator-specific optimization. So quantization is generally useful, and Zihang's going to talk about this later today. But quantization is also necessary to map to the accelerators such as Vita. So Vita requires that input is an 8-bit, at least the current iteration of it. And in order to map to it, we must quantize the network down into 8-bit. So we were able to automatically transform the network with very little accuracy loss. There's another optimization, for example, which fold scale axis, which will take constant scaling factors. So like if you want to multiply a weight matrix by 5, you can't do this on the accelerator because the accelerators don't have scalar multipliers. So what we're going to do is use constant evaluation and some transformation to compute this away up front. And then finally, things like data packing. So again, Vita requires that data is in a 6-dimensional format to invoke certain operators. And so we perform this optimization on the program before mapping it to the accelerator. So finally, the last couple minutes of the talk, I'm going to focus on the backends. So Relay, once we have the IR, we can map to the graph runtime, which is the existing NNVM and TVM runtime. We can map to the interpreter, which I will talk about. And there's an experimental prototype, which we haven't released yet, for doing ahead-of-time compilation. The interpreter and the ahead-of-time compiler can map to both the CPU and the GPU, but only we must use the graph runtime right now to support Vita. Okay. So the goal here was just to implement multiple backends to demonstrate versatility of Relay and the fact that we can support many different execution strategies, and we encourage people to come and try some new ones. We're still working on the design of a new sort of runtime system for all of Relay's features, and so this is part of the experiment for us. As you know, many of you have already used TVM. I can now take, the way operator compilation works is I take a Relay program or a computation graph, I extract the set of operators, I feed it into TVM, I get a shared library out. Once I've done that, I can execute on the graph runtime today. So what we'll do is we can just map a subset of Relay programs onto the graph runtime directly. So you can use this existing functionality if you know how to execute with this, or any compatible executor. The interpreter is actually a reference interpreter for Relay, so the goal of this is not to be necessarily the most efficient, but to demonstrate that we can execute all of Relay. One interesting part of this is that we use JIT compilation for operators, so when you see an operator invocation in a Relay program, we will JIT compile it via TVM. So you actually get pretty decent performance just on this. And then finally, there's an ahead-of-time compiler, which I'm going to skip over in this sort of time. But at the high level, the goal here is that we can take Relay IR and we can generate a blob of C++, compile this down, and execute it directly in device with no other dependencies. So this works on CPU and GPU, and it just links against the TVM as a dependency. So you can see a brief diagram of this. And we just go through a standard pipeline, a couple different passes. We emit C++ code to Clang. We get a shared library out. And when you call compile in Python, you'll get a Python function. And one of the cool things about this ahead-of-time compiler was it was just implemented as a pure Python library that uses Relay as a dependency. So like I said, we support Vita. Here's Vita. I just want to skip to the evaluation. So at the high level, one thing that I want to show is that this is, I think, one of the most interesting results to take away from the talk, is that the very top level boundary is when we just interpret the cell, the RNN cell in Relay. And you can see as we move more and more of the program, so the orange line is us compiling, so the compiler gives us a small speed up. But as we move the interpretation of the RNN down in this green line right here, so this is when we interpret the cell, it gets much faster. And then you can see PyTorch right here, there's the blue line. And then this red line is when we compile the entire program. So we actually get quite a big speed up by being able to optimize the entire program in one go. Okay. So the CNN results, this is a slightly old graph, which I didn't have time to regenerate, but we're a little bit, so there are a couple data points in here where we are a little bit slower than NNVM. And most of this is due to one missing optimization. So there's this alter layout optimization that was discussed previously by AWS folks, and we just have gained support for that in the last week or so. The main important takeaway result here is there are many devices where we weren't even able to get a benchmark from TensorFlow or TensorFlow XLA. So the cool thing about Relay is that we can support an expressive range of models, and we can map it down to many devices. And then finally, I just wanted to touch on the Vita results. So the cool thing on Vita is that compared to a comparable CPU that we would execute on in an edge device, we show great speed up by mapping down to FPGA. And we now have a generic pipeline that we've been developing from Relay to Vita, and we hope to upstream that in the next week or so. Finally, I just wanted to touch on future work. So as we talked about a little bit this morning, our goal is to evaluate Relay on training tasks next. If people are interested in this, I'd love to talk to you and get some feedback on what you're interested in and what your use cases are like. Another goal, I think Eddie and a couple other people in the team are to pursue sort of Auto TVM 2.0 by applying Auto TVM to Relay. And then we have a couple other interesting things, like one thing I think is really interesting is NIC's support for different analysis and optimizations for deep learning, such as differential privacy. And with that, I'm just going to wrap up. So Relay is an intermediate representation for optimizing deep learning programs. Our real takeaway insight is that machine learning models are just programs, and how can we apply that insight to bring ideas from PL to machine learning? And this generalization has given us support for a lot of great things. We're really excited about production and research collaboration, so come chat with me, and I'm happy to follow up.
So now we have one talk now on training systems. So we've been hearing a lot about programming models and high-level IRs and compilation for mostly inference, a little bit of training, but related to single node. Now we're going to hear a little bit about distributed training by Liang. Liang.
Hello, everyone. My name is Liang. The original title of this is without that Whirlwind tour. It was because yesterday when I was doing the dry run, people complained it's too much content. So instead of dumping a lot of hard work into changing the content, I decided to change the title. So far, my colleagues been focusing on making sure that a single node TVM stack is as optimized as possible. So this work, we're going to take a look at some of the groundwork that we'll be building to make TVM, or to bring TVM to the distributed world in terms of training and inference, be it in the commercial cloud or in your own cluster. So with that, let me introduce you to the parameter hub. So on a very high level, the parameter hub is an optimized, topology-aware, and a dynamic mechanism for inter-machine communication, or fancy. This work is in collaboration with folks from Sample Lab, the TVM team, and Microsoft Research. So we're going to describe Parameter Hub in this work in the context of cloud-based training, so the techniques we're going to introduce here should all apply to your own cluster. We should all agree that deep learning constitutes an important workload in the cloud today, and I'm not accepting any argument otherwise. And as all major cloud providers have already doubled down on the ecosystem for cloud-based training. Just to give an example how popular this is, I recently learned that according to Facebook, the server demand for DL inference across data centers nearly quadrupled in less than 2 years. Right? This statement sounds suspiciously familiar, and the next time when someone shows me this, I should ask, well, really? Moore's law isn't dead. It's reincarnated. And also, do I need to mention or remind you how many times the EC2 has reclaimed your spot instances just because they run on a GPU, mostly right before a machine learning deadline. Even though you're paying the full price for spot instances, they're still reclaiming your machine. Well, it gets me every time. So what is this popular distributed training? Well, distributed training at a very high level consists of two parts, an independent forward and backward passes followed by a coordinated parameter exchange phase. So the independent forward and backward pass usually is run on the worker. In this phase, it's computationally expensive, and the workers will generate gradients that's used to update the current model. So what are gradients? The gradients, you can think of them just as an array of floating points, right, or other representations. Once we have those gradients, the worker will communicate with the parameter server. The parameter server is an entity where aggregation and optimization is performed. So in the aggregation, we just want to add these gradients together, and then we average them. We take an optimization step using algorithms such as SGD, and we derive the new model, and the next iteration can start. So this coordinated parameter exchange phase is actually the focus of this work. So how is this high-level job description mapped to the context of the cloud today? Well, here we show a few racks in your data center, where machines are organized into racks, and within each rack, machines communicate with each other using a top-of-rack switch. And when it comes to inter-rack communication, the traffic needs to be routed through the network core. When a DL job is launched, the scheduler will pick up some machines with compatible capabilities, such as ones with a GPU, to run them as workers, and some will be designated as parameter servers. When the workers have their gradients, they need to commute with each and every one of the parameter servers. Sounds straightforward, right? What can go wrong? Well, it turns out distributed training, especially distributed training in the cloud, is extremely communication bound. In order to show this, we proved this by running multiple experiments on Amazon EC2 across multiple generations of virtual machines. So the graph on the right, on the x-axis, we have each and every one of these experiments where we have increasingly more recent GPUs. The y-axis shows the time it takes for 8 machines to finish one iteration of ResNet 269 layers training. So lower the better. And within each bar, the golden portion of it will represent the time where both the GPU and the network interface are active, whereas the purple portion of it will represent the time that only the network interface is active. So the system is solely waiting on the network. As you can see here, when we first introduced GPU in the data center back in 2012, it wasn't a big issue, as most of time is spent in waiting on computation. But as we're equipping with faster and faster GPUs, we have shifted the bottleneck from computation to communication to a point where making GPUs faster is going to do little to increase throughput, as is the case when we change the GPU from M60 to Volta 100. So clearly, this is a lot of waste in terms of compute resource. And unfortunately, this phenomenon is not unique to the particular network architecture we just chose, and it's universally observable across all popular neural network architectures. So why is this happening in the first place? Well, the high-level answer is mapping of training of workload to the cloud context is just not optimum. But why is it not optimum? Here we provide 3 major bottlenecks. The first bottleneck comes from the framework itself. What I mean by that is the framework, the design decisions made in the software, prohibits us from actually take full advantage of this hardware. To show this, we profile MXNet's distributed training pipeline, and then we break down this purple bar that you just saw earlier in the graph into further details. And then we highlight each of the overhead with this different shades of purple. So in an ideal world, you want to see all of the purple bars totally collapse with the golden bar, which is computation, fully hiding communication latency. But in reality, we're still seeing overheads coming from other aspects of the pipeline. The second bottleneck comes from there's simply not enough bandwidth when it comes to inter-VM communication or in general machine-to-machine communication. In order to illustrate that, let's ask the question, what is the minimum bandwidth required for each of the popular neural networks in order for communication to not bottleneck computation? I'd like to illustrate this using this thermometer on the right. At the bottom, we have 10 to 25 gigabits speed that I call the cloud bandwidth. At the top, we have terabit connections that I call the dream speed that hopefully one day we can have in data center. Now let's plot the requirements for each of the neural nets. So GoogleNet and Inception is asking for 40 gigabit connections, ResNet 100 gig, and AlexNet more than a terabit of connection. And this is only with 8 workers and a recent GPU of GTX 1080 Ti. Imagine if we have more of them and faster GPUs, this number is going to be up the chart. So as you can see, the number is well exceeding what the cloud provider is providing today. So clearly, there's a bandwidth bottleneck argument there. The third bottleneck really comes to how machines are deployed in the cloud. And the bottleneck comes from this interact communication. In reality, VMs can spawn anywhere in the cloud, spanning multiple clusters. Remember, I said where the interact traffic needs to be routed through the network core? Well, that network core might be experiencing transient congestions or is oversubscribed by design. This means the cross-rack traffic usually has a higher cost than intra-rack communication. So to show this, we run 8 machines on Amazon EC2 with 10 gigabit links. And then we perform a pairwise bandwidth probe. So if you look at the first column, when machine 1 is communicating with machine 2, it can only deliver half of the bandwidth when it's communication with machine 3. So clearly, the machines are forming their own clusters. But unfortunately, this information is neither exposed or probed by existing framework. So algorithms or reduction algorithms built on other assumptions, such as link speed being uniform, is unlikely going to work optimally in a cloud environment. So next, we're going to propose a series of optimizations collectively known as the parameter hub, the co-design software, hardware, and the training cluster itself. So let's visit each one of them. We'll start with the software. Remember, the goal here is we want to eliminate the first bottleneck introduced by the framework by streamlining the DDNN training pipeline. And this is how we do it. The crux of the software optimization can be summarized as follows. Imagine each of us is a processor core, and we have many processor cores. So at any given time, the workers can stream gradients into our memory. So how do we actually organize each core to process the gradients in a locality-preserving and load-balanced manner? Well, in order to answer that question, we built many reduction prototypes. So in each of the experiment, the gray bar represents a gradient array. The arrow with this color represents different core along with direction of aggregation. So it turns out this particular approach, I'm going to highlight here, called the tall approach, really stands out for its performance and is used by Parameter Hub. So let's take a closer look at how the tall approach works. The tall approach starts by chunking the gradients into a series of virtual chunks deterministically. A gradient, a virtual gradient, or a virtual chunk is then mapped to a particular core on a remote server. So virtual gradients can be transferred independently because aggregation and optimization are element-wise operations. We don't need to wait for the entire vector to arrive before we start aggregating. So a chunk is then only processed by a single core, and this is how we maintain locality in the face of aggregation. We then extend or preserve locality across aggregation and optimization by having the parameter hub optimize the same chunk with the same core that does the aggregation. So as you can see, with this approach, or with this tall approach, we're allowing a very fine-grained streaming aggregation and optimization for maximum hiding of communication latency. In fact, we can do single floating point level latency hiding. Okay, now it's time to deal with how we deal with the insufficient bandwidth problem. So instead of investing millions of dollars upgrading to higher capacity links, here we take another approach. We want to reduce the bandwidth required for cross-rack traffic, cross-rack communication using what we call the parameter hub hierarchical reduction. And this is how hierarchical reduction works. So we start with, this is your rack, and we want to designate one of the machines in your rack as the local aggregator. And it would perform a two-step approach. So instead of having the workers transmitting their gradients through the potentially busy network core, they first send their local gradients to their local, aggregator. So involving the first step, it involves only the machines in the same rack. Once each of the aggregator has the gradients, they can start in the second phase, global aggregation. What the benefit of this brings is that since we have already a per rack aggregated gradients, only one single copy of the gradient from each rack needs to be streamed through the network core. So this brings in a drastic n times reduction when it comes to cutting cross-rack traffic. So this is very helpful if we have a busy network core. But wait a minute, you might say, well, if you're an operator in the cloud or if you're building your own cluster, this is totally fine because you know what the machine topology looks like in the network. But what if an end user in the cloud, all you get from the cloud provider is a list of IP addresses? So here we will use the idea of active topology probing to actually uncover what we think is most likely to be the network topology that's powering these VMs. And it works at a very high level like this. So we start with a list of machines on Azure or in C2. We use very accurate probing techniques, such as those powered by DPDK, to derive a distance matrix. So this distance matrix is then fed to a clustering algorithm, which will guess or infer what is the network topology that's powering these VMs. And then we can send this topology to Parameter Hub, which will automatically generate a schedule, a hierarchical reduction plan, like the one I just shown earlier, to adapt to the current non-topology, or the current infer topology. And also bear in mind, this process is continuous. As we monitor the traffic changes in the cloud, our topology, or the infer topology, can evolve with the plan. So we always get some speed up by carefully placing the nodes by carefully classifying the nodes together in different clusters. So adapts to the evolution of the data center traffic. So with all of the optimizations built in, our evaluation on current commercial cloud on EC2 and Azure shows some benefit. So the graph on the right, when compared to Facebook Glue's halving and doubling algorithm, so Facebook Glue is the backend for Caffe 2 and PyTorch when it comes to distributed training. We can achieve about 2.4x speed up in end-to-end training ResNet 50 on Azure and 1.4x on EC2. On the right, we show similar numbers when comparing with a ring reduction such as NCCL. We can see a larger speed up on Azure and the 1.8x on EC2. So all these are run using the configuration below with 32 machines, and the details we can chat afterwards. Last, I want to emphasize is the ease of integration of Parameter Hub. Currently, we have native support for MXNet, and we have support for PyTorch and Caffe 2. And it supports all communication backends, including TCP, InfiniBand, Rocky, and iWarp. So in fact, all you need to do to invoke Parameter Hub is to give us the list of keys and the addresses, and at appropriate locations, call Parameter Hub arrow or reduce. So we're taking care of the rest for you. So that's the end of the software optimization. And hopefully, with Parameter Hub, we can make the TVM stack more complete. But we're not done yet. So imagine if you have the luxury of actually being able to move the cables around in your data center, or you have the power to design your next generation super duper training cluster. We have this exciting thing for you. It's called the hardware parameter hub. So this is what we think an ideal hardware configuration for this workload for deep learning. With the goal of balancing computation and communication resource, this hardware parameter hub, our prototype, features a 10 InfiniBand interfaces delivering up to 500 gigabits of network bandwidth to solve all the 3 bottlenecks I mentioned earlier. To match its 800 gigabits PCIe bandwidth, and is fully supported by our software. In fact, our software is very well tuned for the hardware itself, so that the hardware can deliver up to another 2x speed up over our parameter hub software, and giving us some edge over other solutions. So our analysis shows that a single parameter box or parameter hub hardware can actually support hundreds of workers training ResNet 50 at the same time, deliver up to 35 gigabytes per second of reduction bandwidth. In fact, if you were to build your next generation of data center full of parameter hub hardware, and when it compares to the standard approach, our estimate shows that we can achieve about 25% better training throughput per dollar when it comes to training ResNet 50. So if you're interested in the parameter hub or the parameter hub hardware, you can refer to the detail. You can find the details in our tech report. And that's all from me, and thank you.
All right. Any questions for Liang while we context switch? All right, so I actually have one question. We have people from Amazon and Microsoft here. Can you tell us why you do better in Azure than you do in EC2? Do you have better friends at Microsoft or what? You know?
It depends on who pays us more, I guess. But no. I think it's how the data center network is designed in both in this different environment. I think both are great, but there's just better at other things, at different things. We don't have a detailed understanding of why we're doing slightly better on one versus the other. But one other big aspect I'm considering is because the network pattern or the network utilization at the time that I'm doing experiment might have a big impact on the speed that we can get. So it might be just because of a redundancy, maybe we run 100 times, we might see a similar speed up on both clouds. Because currently I'm just doing maybe an average of 200 iterations. Yes.
Great.
Yeah.
Got it.
Thank you.
Oh, there's one question, right? Very quick.
So I'm Jenny from Amazon. So I have 2 questions. One is that, what is the overhead of getting the network topology? And then the second question is also related to the first one. How do you ensure that the network topology won't change during your training time? Thanks.
So the first question is, what is the impact of network topology? right? So yes, there's a graph that I shown earlier that shows if you're doing cross-rack traffic, cross-rack communication, you might only get half of the bandwidth than the inter-rack communication.
For example, you train for 3 days,
Well,
and then the overhead of
well,
getting
if,
those
if this is
topologies.
if you're training things like AlexNet, then effectively it's 2x, right? Because if it's really communication heavy, then all you do is waiting on communication, and if the speed is divided by half, then the overhead is probably slightly less than 2x. Yes. So the second question is, sorry, I already forgot.
Yeah, how do you ensure the network topology won't change?
Right, so that's
training?
what we call the active topology probing, where we are running this probe continuously as you train. So when we detect something changes a lot, or a link speed also all of a sudden from 5 gig to maybe 10 gig, it's a great time for us to reevaluate and come up with a schedule that actually adapts to the new one. So the parameter hub software can actually deal with dynamic change of schedules, so just to pay a small overhead, but we can deal with that, yeah.
Thank you.
Thank you.
All right, and to conclude this session, we're going to have now a hardcore hardware talk about building supercomputers by Michael Taylor, professor at UW. Michael.
Great. So yeah, I'm going to talk a little bit about a project we've just been ramping up here at UW in collaboration with Cornell. And I guess from the perspective of this workshop, we're designing a supercomputer to run TVM as awesome as TVM can be run. And we're going to use TVM to design the supercomputer as well. Okay? So that's kind of nice. This is a huge effort funded by DARPA with 6 different professors and their research groups. So from the hardware perspective, there's a lot of stuff going on. Hardware is a super exciting area to do research in these days because well, a lot of the things that we held true are changing. End of Moore's law is coming. Dennard scaling, which refers to the energy efficiency of computation improving. That has ended a decade ago before the iPhone had even been released. And architects in general have decided that the solution to these energy problems is to specialize the hardware, to have very specialized hardware. And GPUs represent a kind of a midpoint in specialization, but there's even more extreme forms of specialization that are coming down the road. And so the graph there that you see is the process nodes of different transistor sizes over time. And basically, it's been new nodes are coming out less and less often. And Intel has been stalled out for a while on the last node that they've been working on. So, in terms of kind of new directions for architecture and in improvements in what humanity can compute, it's really focused around specialization, coming up with special purpose hardware. And some of the key kind of ideas in the HammerBlade project are around these questions about how you do specialization. And we think that moving from a human-centric computational abstraction hierarchy to an ML-centric computation abstraction hierarchy is a solution to doing this. So basically, in the old world, we have language, compiler, instruction set, microarchitecture, hardware description language, and CAD tools. So we want to blur these abstraction layers. And so the idea is that at some level, we've created these abstraction layers to keep things simple for humans to reason about. But if we're applying ML to the problem of designing computers, then we need layers that make sense for ML. And so we are envisioning, this supercomputer we're building is going to have ML co-designing the hardware and software to run ML, and also graphs are a kind of programmatic requirement of DARPA, and so we're looking at graphs as well, and both ML and graphs together kind of comprise some of the most challenging workloads for computers. So we're going to basically be leveraging specialization and using basically, part of the challenges is how do we, in order to use ML, we need to decompose the system into building blocks that have knobs that ML can tune. And so that's part of the challenge that we're looking at is how we re-architect, how we build a computer by creating layers that have these knobs and that ML can apply itself to. And so there's a couple pictures of the architecture I want to show you. So one of the key building blocks that we're using is what we call a tile that has a tiny processor that's very functional plus some ML-tuned fabrics. And then those processors are connected by a variety of on-chip networks. And then we can scale it out. So basically, this chip that we're targeting has 4,000 processors that are focused on the kind of hardcore dense compute, and then a bunch of Linux-capable cores to run the kind of more random twisty code. And we've been starting as a baseline, we've used this chip we built, which was called Celerity, which we taped out in 16 nanometer. And Celerity broke the world record in RISC-V performance. Last year, we hit 500 billion RISC-V operations per second in 16 nanometer. And you can actually fit 50 RISC-V cores in 1 millimeter in the Celerity chip. And so we're taking Celerity as a baseline, but then extending it to make it interface better with TVM, and adding in essentially programmability features into the new design. We've actually made a fair bit of progress. So this is a design that we've just recently been working on, and we'll be sending out to the fab for TSMC 40, which is an early HammerBlade prototype. And then if you zoom out in the system from the ASIC, at the next level, we're connected to Xilinx FPGA. And we're using the Xilinx FPGA both for access to high bandwidth memory, which is the lowest energy DRAM that's available today, and also to many communication links. So in the last talk, we talked about how essential it was to have high bandwidth links. And so each of these boards that we're building has the equivalent of 1,900 gigabit interfaces that connect to the other boards. And then we take those boards and connect them up into a chassis. And then those chassis connect up into a rack, and then potentially we can take racks and connect them up into a data center scale like Catapult. And then one of the key primitives is the sort of integration of the communication resources of the Xilinx FPGA and also the memory resources so that we can reshape memory on the fly for the most convenient layout that's necessary for the particular computation that we're doing. So I'm going to jump through a couple of the other aspects on the software side. So we're building a full software stack. For ML, we have, of course, TVM, and then for the graph side of things, we have Graphit, which is a new language for describing graphs from MIT. And then this is decomposed onto this abstraction, new ML-tuned abstraction layers that I mentioned. And of course, we have some of the auto tuning features that Luis has been doing in his research to tune the software stack for the architecture. And then as a kind of interface layer between TVM and the hardware, we've developed with something we call CUDA Lite, which is essentially kind of a new interface that is useful for new classes of accelerators as a kind of stand-in intermediate representation as you develop both the accelerator underneath TVM and as you tune TVM to map to the accelerator. So I'm going to finish up pretty soon. So I mentioned high bandwidth memory as one of the key aspects of the system in terms of getting energy efficiency. And one of our early goals is actually to emulate HammerBlade on Amazon F1. We're interested in getting early users who will basically be programming the HammerBlade system, and they can just use an Amazon F1 image to get early access to our hardware design. So I'm going to wrap up here and take any questions.
Any questions for Michael? So when is it going to be ready?
This is a PI on this too, so I'll ask him.
All right. Yes, Rick.
So once this thing is done, the aggregate throughput that you're expecting for machine learning, the one chip?
What metric do you want to use?
ResNet 50s, or you pick it.
Oh, I see.
Some metric of throughput, yeah.
Yeah, I think we're not quite focused on that level in terms of a throughput target. Our focus is sort of more bottom up, looking at, okay, what is the most energy efficient way to do this computation and yet retain the flexibility of the execution. Maybe Louise, you have some thoughts on answering that question.
Well, we were thinking definitely in the order of hundreds of teraflops per second. So that's sort of like we were thinking teraops per second per chip. So, yeah. And we're gonna have a few of those.
Is that right? Yeah.
Yeah, one more, Raghu.
Hi, yeah. I had a question about your DSLs. You have there was an easy graph and a graphit for graphs. So could you get into a little detail about what that is and what it looks like?
Oh, I see. Your question was on the graph side, though?
Yeah, on the graph side of your software stack.
Yeah, so graphit is a DSL from MIT, Simon Emersinga's group, and our focus is to mostly work with that. But DARPA has a requirement that they want something that's usable by end users. And so, there's something that probably has to sit even above the DSL. Because DSL, like Graphit, is actually still quite low level. Because basically Graphit works, it has kind of the description of the computation you want to do and then the description of the meta information about how you want to map the computation. And so DARPA was talking about, having a bunch of, statistics grad students from NYU try to use the language, and it seemed like, well, this is still a bit lower level than their target. So.
All right, let's thank Michael one more time. Okay, thank you.